and now recording audio through USB mic. You see, it works. All right, okay. Hello and welcome everybody to our April meeting of the Nashville Java User Group. And we have Denis with us that he will introduce himself in a minute. We are your hosts. There is Kate, Phil, I'm Baruch. Evgeny is not with us this month. Thank you, Gradle, for sponsoring the pizza and the food and the t-shirts and the swag and everything else. Thanks, Java Community Process, for swag. Thank you, Greater Nashville Technology Council, for hosting us this month. O'Reilly for the books, and JetBrain for the licenses that we will all raffle in the end of our talk. Next month, we're going to have a lot of content. We have two speakers that will speak about your career. Clay, who is associate recruiter in Waco, will present how the recruiters see people who are looking for a job right now. And Heather is going to talk about how to build your career in Java in general. And we have a surprising appearance of Sergey Gorov, who is now VP of Product and Engineering Test at Docker Inc., which means he used to have a company that was built around test containers that called Atomic Jar, and now Docker acquired them, so he's in Docker going to speak about test containers with us. So that was my part. Thank you very much. And now, Denis.
All right. Now we should have a problem with my laptop.
No, you won't have any problem with your head.
Yeah, the tech is awesome.
Yeah, the tech is absolutely awesome. It's Java meetup. Of course, it's awesome.
It's awesome. 1, 2, 3.
There we go. Magic. You see? Perfect.
All right. Hello, folks. Thanks for coming. The session is about multi-region applications. And throughout the session, we are going to figure out why would the one decide to build those multi-region applications. And then we will try to build our own multi-region application today. So I don't have any slides. This, text file is the only slides I have, because I just want to go hands-on with you. And if throughout this conversation and this demo you find this topic relevant for you, then you will be able to Google and find the content and materials that were created by people that are smarter than me, I hope. So, my name is, why do I give this presentation? My name is Denis Magda. You can find me on social media, Twitter, or whatever. And the last 8 or even 9 years, I've been building and working with distributed application systems, and in particular with databases. And what I see usually when you design those distributed systems or design distributed applications, an application that need to be deployed across multiple regions or data centers or availability zones, then inevitably those applications have to deal with the data access. Because usually what I see is that you are getting most of the problems, latency problems or availability problems with those applications if you don't work with your database properly. That's why databases become our inevitable topic of distributed applications, so the way how you access your data. So the agenda for today, let's make the font size is tiny.
Yeah, that's better.
Yeah, much better. Who cares? Why would the one build multi-region applications? And I define 3 reasons. The first one should be obvious. It's high availability. Let's say that you are building some mission critical application, some important and valuable application. And if that application goes down, you will probably have a lot of headache, or the company will let you go. And with high availability, you take and deploy your application across several data centers or regions. And if any of those regions or data centers goes down, not a problem. Your application will continue serving the customer traffic. The other reason that might sound a little bit counterintuitive is low latency. Low latency for reads and or writes. Why counterintuitive? Because usually when you start thinking about a multi-region application, and imagine the East Coast and the West Coast, like San Francisco and New York, if you deploy your application across those regions that you might think, all right, then the latency should be high, not low. Why? Because the regions are very far apart from each other. But in fact, If you know how to arrange those instances and how those instances are going to consume and serve your data, then you will be able to achieve the low latency. And finally, these days, with the tightened data regulatory requirements, data residency becomes one of the reasons. Data residency, not this way. It sounds like data, you need to comply, compliance with data residency regulatory requirements. Why? Because you might have customers who live in the United States, you might have customers who live in Asia, Singapore, or India, or you might have someone who lives in Europe where we have GDPR, General Data Protection Regulations requirement. And when you build an application for those types of use cases, then you also need to make sure that the users, customers, work with the data and work with those application instances that are running in the regions of their residency. So those are three regions. Why would the one decide to build a multi-region application that spans several locations? The first one is high availability, then low latency, and finally compliance with data regulatory requirements. Today, we're not going to talk about all of them. I want to focus on the latency. So what we want to do next? Next, we are switching to this hands-on session. We are going to build a Java backend for global pizza company. We have a few pizzas left. That's why the topic is very relevant. So what we are going to do first, as every developer, we will start in our local developer environment on my laptop. We will create a prototype on a local laptop. Then we will launch the first version of this application for the customers who live in New York. Let's say launching the app in the US East Coast. Then we will see what's going to happen when we are launching this app in Europe and Australia. And the focus again on their low latency. And throughout this conversation, we will see that the latency first is going to be very bad for those who live, let's say, in Europe, Australia. We will use the latency for those who live in the United States East Coast as a baseline, but then we will play with several, configuration settings for our databases to figure out how to achieve the same low latency for the customers regardless of their location. Sounds good? And by the way, don't hesitate to stop me, interrupt me, because I will be primarily with my heads down, trying to show you stuff. If any burning question, just, hey, Denis, what's going on? Explain more. The application. Let's save this. So where is my application? I need to go to the downloads folder. We have this pizza company, pizza application. Let's open it in the Visual Studio Code. Next, let's make the font size bigger. Good enough? Can you read it? So what this application comprises several microservices. The first one is the kitchen microservice. What this kitchen microservice does, let's say you want to order pizza, you pull up your phone, you put an order, and this order goes into the kitchen. We have a chef, and the chef and his crew will bake the pizza for us. So what that microservice does, it's very primitive. It's very primitive Spring Boot application. It basically has a few REST endpoints where you can put a pizza order and then you can, what else? You can change the pizza status. For instance, the pizza is being baked, the pizza is being delivered, or the pizza was successfully delivered and consumed by the customer. That's the first microservice. The second microservice is called the tracker microservice. And what the tracker microservice does, let's say the pizza is already in the queue and you are waiting for this pizza impatiently. You want to check the status. You open up your mobile phone, you're trying to check the status, and that status goes and handled by the tracker controller. So what it does, the same very primitive Spring Boot application that has the REST endpoint that checks, on the status, like that's my order, what's the status? And the status is primarily retrieved from your database. So the database will store all the information about all the orders that are in the system and about the statuses for those orders. Make sense? So those are two client-facing microservices. And also in this session, I'm using Spring Cloud. I use Spring Discovery Server. What this server allows me to do, all those microservices, when they start, they register with the Discovery service of Spring Cloud. And by doing that, if needed, they can talk to each other directly by using their names, the names of those microservices. They don't need to know, let's say the kitchen microservice doesn't need to know an IP address of the tracker microservice and vice versa. And finally, as you've seen, each microservice has its own, defined API endpoints, REST endpoints. But then I decided I want to use the API gateway of the Spring Cloud. And what this gateway does, the gateway generally, all the requests from, let's say, from your front-end application, from your mobile, will go to that gateway. And then depending on the URL, if I have the kitchen in the URL, those requests are going to be forwarded to the kitchen service. If the URL contains the tracker in the path, then the requests are going to go to the tracker microservice. And this API gateway also registers with the Spring Cloud Discovery Server. And by doing that, this is how I can talk to any microservice, because they are all registered. And when I need to forward, let's say, an API request from the gateway to one of the services, I just need to know the name of the service. If I have multiple instances of the services, then the Discovery Server will be able to load balance those requests. So this is what's given by the Spring Cloud framework. Now, how I'm going to deploy it, I have a Docker Compose file on my local laptop. So the application, this primitive and simple application is created. I'm starting this Discovery service. I'm starting my kitchen service, the tracker, and finally the gateway. So the kitchen and tracker, they need to access the database. I'm going to use Postgres. And Postgres runs on my local machine. It's already running in Docker. Just vanilla Postgres. No any additions or changes to it. Now, let's go and start it. Any questions so far?
Yeah. Question. All your services are using database or only orders and kitchen?
Only my own, my customer facing, like the kitchen uses Postgres. It's here. And also their tracker service. The Discovery server and the gateway of the Spring Cloud, they don't need it. So we are registered, and by the way, right now you can see this port number. You can go to the Discovery server that runs locally, and you can check the status of your microservices. You can see that they are registered, and right now the gateway will be handling my requests and forwarding the request to a specific service. Now, let's say that we are happy. We developed our first prototype of the application, and our managers are eager to open that first, location, brick and mortar pizza store in New York. We want to test it. How we are going to test it? I'm going to use this, basic HTTP request, because this is what done. HTTP tool. This is, anybody uses it? Yeah. So it's like, yeah, I use it like, I switched to it from curl, because curl is a little bit more low level. HTTP provides a little bit more user-friendly interface for sending HTTP requests. So generally, what I'm going to do, I'm going to send this HTTP GET request to my locally running API gateway. And that request will go to the tracker microservice. I just want to get all the orders that are in the system. So yeah, we don't have any orders, and what do we see in the result? So the result for every request that we are going to send, it will print the result in the following JSON field. But also to every result, I'm adding the following field, the database latency. This is the latency between your application backend, that is processing the specific request and your database. And the whole purpose of when you primarily, what I see, when you're building those multi-region applications, primarily, and if you're focused on the low latency aspects, you would be dealing with the latency that is between your application backend and your, let's say, data system. It can be database, it can be, let's say, some Kafka, cluster, it can be anything else. And that latency will depend on how far your backend instance from your database and what's the network latency, right, between those services. So today we are going to focus and optimize this specific parameter. Next, let's go ahead and put the first pizza order in the system. The order ID is going to be 1, and we are saying that we are opening in New York. Let's put the first order. It's done. Let's do second. Created. So that's the result, and it took us 5 milliseconds to add this order into the database, and the database runs locally on my laptop. So good enough. Also, another request that we are going to use frequently today in a real cloud environment is the GET request. We are connecting to the tracker, and I want to check the status for a specific order. Let's say order ID New York. So it all works, and when you execute it a couple of times, yeah, the latency is also very small. Now, that's the prototype. So this is how the application looks like. Now, what I want to do next is to switch to a real cloud environment. I deployed I provisioned 3 virtual machines. One of them is in the United States East Coast, somewhere in Northern Virginia, I guess.
Zoom in, sorry.
Okay, this way? Better? Okay. Another one is in Europe, it's in Frankfurt, and the last one is in Australia. It's close to Sydney, I guess. So what we are going to do, we are going to take this application with all of those microservices and deploy in every location. And then we are going to emulate a customer, let's say. We are going to play the roles of the customers who live in New York or in Berlin or in Australia, and want to see what's going to be their customer experience. And the customer experience is going to be driven by the latency. As for the database, for my local prototype, I was using Postgres. For my multi-region deployments, I'm going to use Yuga by DB. I've already have a few instances running. So what's Yuga by DB is a quick introduction. Yuga by DB belongs to the PostgreSQL ecosystem. So it's a distributed Postgres. So if you want to deploy, if you need Postgres that scales and never fails, that's Yuga by DB. You run it usually in a multi-node configuration. And by doing that, you will be able to scale your data across required locations. You will be able to scale reads and writes. And also you can tolerate various outages. So that's the database for our experiments today. And also the good part, it's Postgres compatible, it's feature and runtime compatible with Postgres, not 100% compatible, because the only 100% compatible database with Postgres is Postgres. The other compatible databases like Aurora, AlloyDB, or Yugabyte, they are highly compatible with Postgres, because we use Yuga by DB uses Postgres source code, so the query layer of Yuga by DB is Postgres, but the storage layer is what makes Yuga by DB unique. So you are effectively still connecting to Postgres, but the Postgres right now runs in a shared nothing configuration. So for our first experiments, how our database configuration looks like, let me show you. I deployed a 3-node cluster across 3 regions in the United States. We have 2 nodes in the United States, East 1 and East 4. This should be, I think, South Carolina. And this is Northern Virginia. Yeah, it's opposite, South Carolina and Northern Virginia. And then we have another one is in Iowa, United States Central one. Why I deployed multi-region configuration? Large fonts, okay, this way? Can I hide? I probably cannot hide this one. But anyway, why I deployed in a multi-region configuration? Just because probably I want to tolerate region-level outages. So the data, when you will be sending any changes to this database, the data is going to be replicated synchronously across all of those regions. You will see the real latency, what the latency impact would be. But you are free to deploy across several availability zones. You can pick just one region and deploy across several availability zones, or you can deploy in all the other configurations. It's up to you. It's up to your high availability requirements. Now, Let's quickly connect to the following application instance. Let's finally deploy our application in the United States East 1. I copy the IP address. I show you all the instructions. SSH, we need to SSH there. I need to go to, let's go here. We want to SSH to Google. I have my certificate so that nobody needs to see my passwords. At least I remember the passphrase. It's easy. And now let me change the title of the terminal. It's going to be USA.
So you're using public IP address, right?
Yeah, I SSH to the following virtual machine right now in Northern Virginia. And what I'm going to do, I'm going to start the same application instance that we tested locally on my laptop. And we will start looking at the latency. This application instance is going to connect to the following database cluster. It's a 3-node cluster with every node running in one of the regions. So I want you to witness that latency. What does it mean to run in this configuration? Make sense? Good? Okay, so the scripts. What is it? Yeah, the same application that we played with. But for the sake to save the time, I created, several scripts. And what those scripts do, I'll show you. I think today it's safe to show the contents because I have a password hard-coded there, but it's fine. I'm going to shut down those VMs. So when that application is going to start, it's also going to use that Docker Compose file. Into the Docker Compose file, I'm passing this as my database address. You're going to connect to Yuga by DB instance in the United States East 1 code, but you're going to use the same PostgreSQL driver. Like the application, I don't have any application code level changes, and then let's say SSL and password, etc. And if those services are already running, I will ask Docker Compose to restart those tracker and kitchen. So generally, throughout this presentation, I'm going to use several versions of this script that starts, and the only one difference in those scripts will be the database connection endpoint. Okay, so that's the only one difference. Now, let me do this starting United States, East Coast. Okay, looks like I had a rehearsal session before this meetup, so that's why we had to restart our application instances. Looks like the discovery service, the Spring, we're starting the microservices. While this is happening, let's actually go and check that. Let's take this IP address. And I can connect to this IP address and, no, I don't need this. 8761. So that's the same Spring Cloud. It's called Spring Eureka. That's the internal name. So all my services are running, but right now they're running in the cloud, in the real cloud environment. Okay, so now let's run the same API call. So the API calls are going to be executed. I'm going to connect to the locally running instance of this tracker microservice and asking, hey, please return me all the orders that you have in the system. So generally, the latency time is going to be 6 milliseconds. And this is for that multi-region cluster. How does it work? The primary, it's connected to this database, the database node. The database node has, the consistent copy of the data, and they are located in the same availability zone, which the latency is around 5 milliseconds. Now, the application is launched, and we've got our first customer, lucky customer, who lives in New York, and that customer wants to order pizza. Let's do this a few times because I want their connection pools, the database connection pool to warm up. But you will see that on average, the latency time is going to be around 20 milliseconds to write this to the database. Why 20 milliseconds? For the following configuration, because primarily the thing is related to the database. I have this 3-node cluster that runs across 3 regions. And I'm connected to the following location. But then, from this location, this node needs to start a distributed transaction. And it uses the Raft consensus protocol to replicate changes to the United States, to Virginia, and to Iowa. When you use the Raft Consensus Protocol or Paxos or another protocol, then at least you need to get a quorum of 2 nodes. It's highly likely that the node from the East 4 region will respond sooner than the one from Central. And that's why the latency is 20 milliseconds. I guess that the latency between East 1 region and East 4 is around, let's say, 15 milliseconds or 20 milliseconds. The latency between East 1 and Central 1 is probably around 30 milliseconds, 35. But generally, once this transaction is acknowledged, you have a consistent view of copy of your data. And if any of these regions goes down, you still have the consistent copy of your data. But if you want to bring this latency down, you just probably need to deploy across multiple availability zones, but within a single region. It all depends on your latency and high availability requirements. Now, but what's about reads? I have this order in the system, and you remember that we have another HTTP request that we can send to the tracker microservice. And now I'm telling, okay, I've ordered this pizza 5 minutes ago. What's the status? Let's execute it a few times and let's check the status for the second pizza. The latency is around 4 milliseconds. Why? Because in this case, we are connected to this database node in the United States East 1. We know that their data is consistent, etc. And it's really fast, 4 milliseconds. And let's say we launch this application, and this location in New York is growing rapidly fast, and the management team, can't wait to launch this pizza service in other locations, and they decided to experiment in Berlin. For that, the first step is we, the application developers, we already have this application backend that is written in Java. And if we want to make this backend available in other locations, all we need to do is to take this application and deploy it in a region in Europe. Let's say we are opening location in Berlin. And then we will do the same for Australia. Also, and this is going to be the easiest part. It's very easy to deploy those application instances in those locations. Once you have, let's say, application instances running in United States, Europe, or Australia, or other locations, your next step probably would be is to set up a global cloud load balancer. Why would you do that? Because today, what I'm doing, I am emulating that customer experience by connecting to those virtual VMs that are deployed in a specific location. But when you will be running in production, let's say you have a customer who lives in Berlin. The customer just takes this phone, goes to order the pizza. The mobile phone will be connected to one IP address that is provided by a global cloud load balancer. And that load balancer will see, okay, this connection is coming from Berlin. What's the closest application instance? It will detect that the closest application instance is in Berlin. And that's it. The request from the customer will be automatically routed to that location in Berlin. And from there, you are responsible for the rest of the interaction. You decide where to get the data from or where to put the data to. Okay? So makes sense? We are not going to discuss this global load balancers, but if you are interested, it's a super cool thing. If you're using, let's say, Google, Azure, or AWS, every major cloud environment supports it. And I think that OpenShift, Red Hat OpenShift, and other solutions for private clouds have it in their toolbox. So now let's connect to their instance in Berlin. I'm going to actually split the screen several times. So this part is going to be used for Berlin. Let's do this. Let's rename to Germany. And also, I need probably to do this. Some permissions. I need to give permissions to my local user to start containers in Docker. Sometimes it's required, sometimes it's not. And also, I'm connecting to their instance in Australia. It's very simple stuff.
What's the purpose to connect remotely to the instances?
Huh?
What the main goal to connect remotely to the instance?
The latency, to emulate the experience of the customer. Yeah, so you'll see it. Australia. Okay, we're in. Now, every instance has the same application deployed. And what we are going to do now, what I have this pizza company working, and we know that my database right now where? In the United States. Let's try to see what's going to be the experience for those who live in Germany. They also need to connect to their, let's connect to the node in the United States East one. We are doing this for Germany. And we are going to repeat the same for our location in Australia. Okay, looks like it connected. Let's run this instance in background. And now I have this instance running. I can send HTTP request to this locally running instance, but that instance is connected to the database that is in the United States. Let's compare the latency. So we remember that when we were doing write requests from New York, when we were ordering pizza from New York, it was taking like 20 milliseconds on average. Let's say that that location in Berlin is opened. And I want to order pizza, and I'm saying that the location is Berlin. Let's do this a few times because I want to warm up caches. I want to warm up connection pools. I'm using Hikari connection pool, and I need to warm it up. So compare the latency. It's 10 times worse. Why? Because I'm connected to the locally running application instance, but the data needs to be stored in the United States. So my write request needs to travel through Europe, under the Atlantic Ocean, through the cables, and then it will go to the United States, and it's going to be replicated across 3 regions in the United States. That's why 200 milliseconds. What happens if you want to order a pizza from Sydney? It's obvious that the latency is going to be higher, but the question is how much higher? Let's do this a few times. It's around 400 milliseconds. Why? Because, I don't know, probably this request goes through Pacific Ocean and then from the west coast to the east coast or in the other direction. Anyway, it's 2 times worse than in Europe, and it's, I don't know, 40 times worse than when we have customers in New York. When you have like a small application, when your application doesn't have huge load, probably that's not a big deal. But if, let's say, you have hundreds of requests or even thousands of requests per second, then it's going to be a big problem. Nevertheless, that's the write latency. We have something to work on, but primarily when we, let's say, many applications, they usually have more reads than writes, meaning that the pizza service, before we order a pizza, what we are going to do? We are going to read data. We are going to connect. We are going to check the menu. Probably we are going to build our pizza. So we are going to send a lot of the reads, which means that primarily when you scale to distant locations, initially many of us want to optimize reads requests. So what are the reads right now? If you remember, let's check what were the read latency for those who live in New York. Yeah, the latency was around 4 milliseconds because the data lives locally. If I am in Berlin, okay, I ordered this pizza 10, and my location is Berlin. Let's do this a few times. It's pretty much the same. It's comparable to the write latency. It's around 200 milliseconds because why? The order is stored in the United States, and I need to get there to get the golden copy of this data. How about Australia? Yeah, it's close to 100 milliseconds. So obvious stuff, but at least I wanted you to see how it looks in action. So now my challenge, let's say that we don't like this read latency, because this is a big bottleneck. And this is our baseline. How can we get to this latency across all of those locations, regardless of where our customers live? And it's obvious that, yeah, there is the network latency associated. You need to first send this request to the database across a distant location and then deliver this data back from the database. You need to do something with the database. You need to make this data available locally. And when you build those global applications, there is no any silver bullet solution. It all depends on your requirements. It can be related to your high availability requirements. It can be related to your data residency requirements. It also can be related, are you ready to have any data lag or data lag, because sometimes it's good enough to use asynchronous replication. And generally, we at Yugabyte, what we do, we work with many customers who deploy applications across zones and data centers and regions, and we defined at least 8 design patterns for your applications. You pick one of those patterns depending on your application needs. What we are going to look into today. First, I want to start with one of the most well-known patterns. Let's say if you want to optimize read requests, then the obvious part is we can use read replicas, replica nodes, any database technology. Let it be Oracle, SQL Server, IBM DB2, Postgres, or Yugabyte DB. We support read replicas. And this is a wonderful toolbox. It's a wonderful tool in our developer toolbox, okay? Why don't we start with it? Because it's obvious choice. Yugabyte DB also supports it. And here is, if I scroll down, this is my primary cluster that we are using right now. I have those primary nodes that run in the United States. But also I provisioned read replicas. I have one database replica in Frankfurt, in the same region where I have my application instance, and another one is in Sydney, in Australia. Let's use those replicas and see how their latency improves. What we are going to do, I'm going to run the following scripts. I'm going to restart my application instances and get them connected to the closest replicas. For instance, that's the script that will restart my instance in Europe, and that instance in Europe is going to be connected to the replica node of the database in the same location. And the same stands true for the instance in Australia that is going to be connected to the local replica. Now, let's do Frankfurt replica, restarting. And here is, we are doing restart, but we are connecting to Sydney replica node. Okay, looks like the flight is normal. Waiting for all of the microservices to start. Okay, let's try. With the replicas, yeah, how about we send this request, get all orders. Yeah, the service is unavailable. Probably my microservices, my kitchen and tracker microservices are still registering with the discovery service. Sometimes it takes more time. I know that there are a few parameters on the Spring Cloud end that would make this process faster, but I'm lazy. I artificially introduced this latency. So generally, yeah, we read this, we connected to the replica and we read this data on the replica node. The data was replicated asynchronously from the primary cluster. Now, let's put another order into the system, like order 13th for Berlin. I still can do writes, I still can do updates and inserts from my replica node. The replica node will take this, the database node, it will take this request, but it knows that it cannot keep the data. It will forward this request automatically to the United States. It's going to be stored in the United States, and then from the United States, it's going to be asynchronously replicated back to my replica node. If I repeat this a few times, I guess, yeah, the latency is going to be high because of that. So no any magic. What's good for me as an application developer, I still have one database connection endpoint. My backend connected to this database connection endpoint, and replica node decides if it's a write request, it's going to be forwarded automatically to my database instances in the United States. But that's the latency for writes. How about, let's say, Australia?
When you do writes, does it block until it gets propagated to all databases, or does it just return once it gets written to the United States?
It's a single database first. Like it's a single database, and we have 3 node instance in the United States.
Okay.
And the replica, it's like attached, it's like a follower. It doesn't take part in the Raft consensus protocol. Okay. It's basically, what's being blocked? When your application sends this update, the replica forwards this request to the database nodes in the United States, and it waits while the node from the United States acknowledges that the transaction was committed. And then, but it doesn't mean that this update will be immediately available on the replica, because then at some point, the primary nodes will decide when to send those updates asynchronously.
It's under the hood of Postgres.
Okay. So you do a write read, you might not necessarily get the read back immediately.
Yeah. So generally, like if you try to be just very, if there might be some data like it might be that situation when you just did this write, but then you read it back immediately and it's not visible. Okay. This is one of the requests actually where some of the databases, I know that SQL Server, many other databases, they support this. Like when you're writing through the replica will see its own changes when they're committed, because those updates are sent back from the database node. But we are running in a multi-node configuration, and it's like in that distributed system, it's a little bit hard to predict. Like we want you to see the consistent view of data. Anyway, so this is what we have here. If we repeat this same request, but let's say in...
May I ask a question?
Sure.
Additionally related to what you explained previously. So we have one instance, one request. Classical works everything. We propagate in one instance. Mm-hmm. Then our replicas update all our instances of the database. Fine, pretty fine. But in the real world, we have a lot of application that's trying to write the same transactions. I mean, same records with multiple transactions. So, do you have any limitations? How do you manage this case when you have deadlocks, let's say?
So Yugabyte, same as Postgres. Postgres supports several isolation levels. You have repeatable read committed, serializable. So all of them are supported by YugabyteDB, but they're supported in a multi-node configuration. Let's say that there is some application that tries to update, one of those records. In YugabyteDB, let's say you have 3 nodes. And by default, the data is sharded, meaning that you have your table, and the table will be split into subsets of the data, and every node will be a primary for a subset of your data by default. Which means that there is, let's say, record A, and it's always involved in the transaction, which means that the transaction will be processed by a node that keeps the primary copy for this record. So all the requests will go to that node, and that node will be coordinating updates for that particular record. When you have a transaction that spans multiple nodes, for instance, you're doing a money transfer between accounts. One of the nodes will be coordinating the transaction, but first the changes are going to be written on the nodes that own, let's say, bank account A, bank account B. Once they acknowledge, they also need to replicate it to the follower copies, because in this 3-node configuration, one is primary for my record A, but the other 2 keep the sort of the follower copy of this record in case the primary goes down. So this is how it happens. It's like, but the good thing is that when it's supported, and the Raft, we use the Raft consensus protocol to make sure that if anything breaks the network or any node goes down during a transaction execution, then. Mm-hmm. So what we have is replicas. The write latency is high, right? And this is with Sydney. But the purpose of read replicas is to improve reads. Now, let's say that I put this order, but now I want to get this order back. What was my order? Let's say order 13th. And location is Berlin. During the first actually request, why it takes so much time to execute the first request to this tracker service? The replica node needs to read some system-level metadata from the primary database nodes. And that's why but once the connections are created in the Hikari pool, then the future requests, they're going to be fast. How fast? What's that? It's not fast. Now it's fast. Let me see. 13th. Let's check something else. I don't know. Let's check the other order. Yeah, like 4 milliseconds or 3 milliseconds. It's the same as what we have in New York, okay? Because of data is available locally. If I repeat the same, but for the customers who are in Sydney, it's not a surprise that we should get comparable latency once we warm up our connection pools. And this is actually why I wanted to show all those high latencies during the first connection, because we as developers need to be ready. Right now, Yuga by DB, when you start those replica nodes, it doesn't automatically pull the system metadata from the primary database nodes. There is some improvement that is in progress, but what you do if you restart your application instances, just do a few requests to your database so that the connections are established and all the metadata is available. It's like, yeah, it took a lot. But now, once the metadata is loaded, the data is being delivered, I guess, and you start reading it. What else do I have? Yeah, the latency is going to be comparable. So this is how you improve the user experience. This is how you make the latency low for reads across all of the locations. And you can repeat this pattern for the locations of your choice. You might have customers in Asia, you might have customers in Africa, in Mediterranean, or any other places, or like South America. Just deploy your application instance, and then if you need to improve read replicas might be an obvious choice. But the point with read replicas, again, there will be some data lag. And the data lag depends on the distance between your primary database nodes and your replica nodes. However, for my application, this data lag, but even though you have this data lag, the copy of the data of replicas is always in a consistent state across all of the database tables and all of the objects, which means that you might have some data lag, but whenever you read from the database, you will not have, let's say, you will not see, let's say, that one bank account was already debited, but another account has not been credited yet. So that's not going to happen. What I want to do next? Let's say that I have this cool read latency, but my pizza company keeps growing crazy, and now I want to optimize write latency. Okay? So what we have is for the writes, yeah, the writes are high. It's usually, I think it was between 200 milliseconds or 400 milliseconds. While in the United States, the write latency is right now, 20 milliseconds. When it comes to write latency, write workloads, again, those of us who use the databases for many years, you know that if I have customers in Europe or Australia or United States, the obvious choice is I can deploy independent database instances in every location. And every database instance is going to store data for my local customers and is going to serve the data from those locations. If I need to replicate any data between those standalone database instances, then I will be using an asynchronous replication. As any other database, Yuga by DB also supports those deployment patterns. We call them active-active single master or active-active multi-master. Multi-master means that you might have two standalone Yuga by DB instances, multi-node running in different locations, and you can replicate changes asynchronously if you will. But you will be able to get low latency reads and writes. Single master means that one of those databases is primary, meaning that it basically serves reads and writes, but another one is secondary. It's just for the blue-green deployments. We are not going to test this use case because this is what you can achieve with any database. Instead of today, I want to show you how to achieve this low latency reads and writes with a deployment pattern that is unique to distributed SQL databases. Yuga by DB supports TIDB, Google Spanner, and other distributed SQL databases. So how this geo-partitioning works? Let me jump here because here I have another cluster. It's called geo-distributed cluster. And by the way, today I'm using Yuga by DB managed. It's a fully managed service. You just select your regions, you deploy it, and you get a connection endpoint. But also what you can do, Yuga by DB, same as Postgres, is fully open source. You just go download it and deploy it whenever you like. You can deploy it on bare metal and Kubernetes in your private environment. You can deploy it on virtual machines in GCP or AWS, whenever you like. I just want to have this managed service experience. So how this cluster looks like. So now, I have a single cluster, a single database that spans Australia, Europe, and the United States. The only one difference, in every of those regions, I have 3 nodes, and those 3 nodes span local availability zones. For instance, in Sydney, I have a node in every availability zone, like Southeast 1B, A, and C. And the same is true for the locations in Europe. 3 nodes across 3 availability zones in Europe, and the same is in the United States. All the data of the customers who live in Sydney will be automatically pinned to the location, to these nodes, to these database nodes. I will show you how we achieve this on the application layer. It's very straightforward configuration. And when you will be, and the data is going to be replicated across these 3 availability zones. With this configuration, I will be able to tolerate zone-level outages in Australia, Frankfurt, or South Carolina. So by default, I will be creating special type of tables, and those tables will be pinning data to one of the locations. How does this work? Let's take a look at the tables configuration. In Postgres, it relies on 2 capabilities of Postgres. The first one is table spaces. So this is the feature of Postgres. The table spaces allow you to store table data on a specific, let's say, disk drive, like SSD or some other location. So you can create a table and you can say, like, hey, this table of Postgres is going to be stored in this, on this disk drive. We reuse the same table spaces capabilities of Postgres for pinning your table data to specific cloud regions and to specific database nodes. So this is one feature that we rely on for this geo-partitioning. And the second feature is partitions. Partitions in Postgres, how they work. This is my pizza order table, just one simple table. So whenever I put an order in the system or read an order status, I'm querying this table. But I created 3 partitions. And partitions in Postgres are regular tables, but they are assigned to your primary table. And Postgres automatically places the data to those partitions based on your configuration. And I'll show you this configuration probably in a minute. First, let's run the experiment. So generally what we're going to have. Right now we have a globally running single database cluster. We have 3 nodes in the United States, 3 nodes in Europe, and 3 nodes in Australia. And then our application instances will be connected to the local nodes. And the database will decide where to place the data based on your customer location. So let's say if you are making an order from Berlin, then this order will be stored in Europe. And the order details for our customer in Berlin will not be replicated to the United States and to Australia. And this way you will be able to achieve the low latency writes and reads. Let's run this experiment, and then we will take a look at the implementation details on the application there. So again, all I need to do is to restart my application. So I'm starting with the United States. I'm asking, please connect to the database instance, to one of the database nodes in the United States. And I'm using this geo-partition cluster that I just showed you. Then I am doing the same for Germany. I'm saying, okay, please restart the application instances. And now you need to connect to the geo-partition cluster. And specifically, the application instance needs to connect to the database node, to one of the database nodes in Frankfurt. I have 3 database nodes in Frankfurt, and the application instance will connect to one of them. And finally, we are repeating the same exercise for our node in Australia. Okay, cool. This one is ready. Let's check, do we have any orders in the system? No, we are still registering with the discovery service, with the locally running. It takes more time. How about you? No, United States is not ready yet. Germany seems to be connected, but with this geo-partition cluster, it also takes more time to warm up connection, like system metadata, to load the system metadata from the database nodes in the United States. In this geo-partition cluster, The pizza orders table is going to be geo-partitioned, meaning that depending on your location, the chunks of the data will be stored in a specific place, but there might be some tables, including the system tables, whose copy can be stored across all of those locations. And when you start your application instances, in some of the locations, the system metadata from the database needs to be pulled from the United States. That's why the high latency. So what's happening here? Yeah, looks like we are done. So now, when I'm executing this request, I'm actually trying to get all the orders from the system. Why it takes 3 seconds? Because before, when I was executing this same request over the database nodes that were deployed just in the United States, it was taking how much? Like probably like 20 milliseconds or 10 milliseconds, 5 milliseconds. The thing right now is that I'm running this geo-partition cluster. And the database knows that I have the data stored in all of the locations, and I'm not specifying any city. So which means that my database needs to connect to all of the database nodes and try to pull the information. So that's why the high latency. However, let's run the write request. I am putting the first order for New York. Let's do this a few times. So now the latency is around 6 milliseconds. Why 6 milliseconds? Because this is the application instance in the United States East. I'm connected to the United States East node, and I run 3 nodes in this region across 3 availability zones. So generally, I need to execute this distributed transaction, and the changes needs to be replicated across 3 zones. The latency between the zones within a single region is usually around 5 milliseconds. So that's why 6 milliseconds on average. If I do the same experiment for Germany, let's do, I don't know, order number 10 for Berlin. Again, during the first, when I'm opening the very first connections, it will take more time, but then it's going to be extremely fast. Let's do the same for Sydney. Let's do order 11 for Germany, order 12. So now the latency, took a look. The write latency became the same. Why? Because this data for this order in Berlin, it's stored in Europe. It's not replicated to the United States and Australia. And this is not a replica, meaning that you always see the latest, greatest consistent copy of your data when you're doing writes or reads from this location. With Sydney, yeah, let's do this a couple of times, and you will see that, cool. So the latency is now comparable, the write latency is comparable across all of those locations. How about reads? We should not have any difference. Let's run the read request. Let's say I have New York, like order 2. It's like 5 milliseconds as it used to be. If we do it here, order number 10 for Berlin. Again, I'm connecting to the tracker service, I think, for the first time. And now, yeah, it takes time to open the to warm up the connection pool. But once it's done, also let's do the same for Sydney, because during the first request, it will take time, but then it's going to be all right. And I'm reading this data, and you can see that the latency is comparable, like 3 milliseconds for reads. Sydney is still pulling, some system-level metadata of the database from the United States. So let's wait. Yeah, but once the connections are warmed up, you can see that we achieved it. So we made it. So now we have this application that runs across multiple regions, United States, Europe, and Australia, and we achieved low latency reads and writes across all of those locations. And we can tolerate zone-level outages in every location. This is my database configuration. How the database knows where to put the data? Because if I go, let's say, to my application, let's take this kitchen microservice, like kitchen controller. When I put the order into my database, post, order, ID, location, this is what I was doing from my command line. I'm basically executing this insert into the database. There is no any magic. Like the application is super easy. The application code looks this way, but this is how the schema looks like for this type of deployment, geo-partitioned. I created these 3 table spaces. This is the feature of Postgres. I'm just telling, okay, the first table space is for the United States. This is my cloud, this is my region, and at least this is my zone. I need to have at least 1 copy of the data in that zone. And then I have comparable configuration for the database nodes in Europe and Australia. So this is how I configure table spaces. And then I'm creating this pizza table. I just have 1 table in this configuration, but this pizza table is partitioned, the feature of Postgres, and it's partitioned by the value of the location that we pass in our terminal. So how does it work? If, let's say, the location is set to New York, this is what I was doing here, right? Then the database will automatically put this data into the pizza order partition, and that pizza order partition is mapped to the table space United States. And in that table space, we have 3 nodes running, okay? And the same is true for if the order is Berlin. If the order is for Berlin, it goes to the European partition, to this table space, and the same for Sydney. That's all you need to do. Once you do this, then you just get connected to the right nodes to achieve the lowest latency, and the database will automatically load balance your request and will store your data properly whenever it's needed. And finally, the cool thing that I want to show you is that, let's say that it can happen that you have this, right now I have each application instance is connected to one of the database nodes that is the closest. But let's say that that's the life. Imagine that I am the customer of this company. I live in New York, and I'm traveling to Berlin. And then it's late evening in Germany, and my wife gives me a call and says, hey, could you please order a pizza for us using your account? I'm in Germany. I pull up my phone. The load balancer, the global load balancer, connects me to this instance of the application in Germany. And I'm trying to put the order, and this instance is connected to the database nodes in Europe, not in the United States. But what happens? Let's see. I'm doing this put request from Germany. I want to order, pizza, but for the location in New York. The order succeeds, no any problems. So the application doesn't need to know how to connect to the United States. The latency is obviously will be higher. Obviously will be higher. Why? Because the laws of physics. But the cool thing is that the application code is not complicated. The application is always connected to one of the database nodes, and then the database decides where to route the request. So generally, in this case, I was connected to the database node in Europe, but I wanted to put an order for a customer for my family in New York. The database node in Europe figure out, okay, this order is for Berlin, and as long as this order is for Berlin, we have this table space, the YugaByteDB forwarded this request to the nodes in the United States, and those nodes executed the distributed transaction, and the order information was stored in the United States. It's not stored in Europe. And then let's say that my family doesn't give me a break, and they asking, okay, what's their order status? No any changes, you execute these read requests from the same location. You are saying, yeah, that was the order for New York. I'm getting it back, the status, and just, the latency will be higher. That's it. Why I always specify, let's say, the location. This is important for the geo-partition deployment. For instance, when I'm checking the order status for this order in New York, the latency is 5 milliseconds because I'm connected to their databases in the United States and the data is here. And you're giving a hint to your database. You're telling, hey, the location is New York, and the database knows that I need to go to this partition, and this partition is deployed on this database node. But if suddenly, for any reason, you don't know the location, or you just forgot to add this location to your request, like only the ID, this request will be successfully executed. but you will get the consistent copy of the data, but it will take much more time. Why? Because the database doesn't know where the data lives. You have not specified this location, and the database had to send this request to the nodes in the United States, Europe, Australia. Obviously, we know that the data was stored in the United States, but the database had to check with the other locations as well. So this is how it works. Feel fun building multi-region applications, because those applications you build to achieve either latency, to achieve low latency, and this is what we were focused on today, or you also do this to become highly available or to comply with data regulatory requirements. What we did today, we tried to experiment with the latency, and by creating and experimenting with a pizza company, we deployed it across several locations, and you saw that there are many ways how you can achieve low latency reads and writes. We played with read replicas to achieve the low latency reads, but we had some data lag. And then we also looked at the geo-partition deployment mode that is supported by modern distributed SQL databases. So keep those tools in the back of your mind, and if you ever decide to build those apps that scale distant locations, it's not that difficult. You just keep writing, the application code that might work perfectly fine for both single server database instances or multi-node database deployments. And the databases will be your friends. They will make your life easier by figuring out how to distribute requests and how to replicate the data. Thanks for coming.
Good question. Mm-hmm. With the way you have it currently set up, you're writing the guy in Berlin ordering the pizza in New York. Does the data actually ever get replicated to Europe, or is it just the request gets routed, but does it just get routed to New York?
It's never replicated to Europe. Okay. And probably what we can try to do is let me connect to the data.
It's interesting for if you brought up regulatory early on or contractual too, I've come across situations where there's data in Europe that you can't have outside of Europe.
Exactly. So
you can kind of protect yourself from that.
Exactly, and this is another bonus that you're getting with this geo-partition cluster, because I focused on the low latency, but also you can achieve that low latency reads and writes only if the data is stored locally. It's not replicated. So I'm connected to my YugaByteDB cluster. And let's take a look at the tables. You see this pizza order table. So let's say that first the structure of this table, pizza order. Yeah, I have these 3 partitions. Okay. So what we can do, you can also query these partitions directly. Let me show you how Postgres and YugaByteDB work. Let's say explain, analyze, select from pizza order where ID is 1. So what happens this way? When you select and you do not specify the location, look what the database does. It will be doing the index scan because it's indexed across all of those partitions. So I'm querying this, just table, but the database internally knows. When I know the location, let's say, and location, how to hide you? And location is New York. Sorry, it needs to be this way. Then the database is smart, right? It's not going to query other locations. And the same is relevant for write requests. What if we do this, explain? I can actually do explain. Yeah, we can do it differently. Let's imagine the time in Europe. Let's query all the pizza orders, pizza order where location Berlin. So we're getting these 3 orders. those three orders are retrieved from the European partition. What I want to do next? Let's say that I want to insert a new order, pizza. Pizza order values. Let the order ID be, I don't know, 100. So what's the structure? I need to specify ID, location, just ID and location. The time is going to be generated. It's going to be 100 and the location is Berlin. Status, okay, and the status, I think needs to be ordered. Or ordered. Let me do this. We're almost there. Okay, we inserted it, and now let's query our data from Europe. We see it here, right? And you can even query it directly. You can query your partition directly. You can specify this name, Europe. It's here, right? 100. Now, let's try to do the same experiment, but your original question, it took a while to get to this answer, but I wanted you to see it. Was this order replicated to the other locations? Let's query United States partition. No, we don't have any data. Yeah, you're right. We need to remove this one. It's going to be fair. We don't have it. And Australia. Also, we don't have it. So this is how you can also achieve the data regulatory requirements. Again, the application doesn't need to be bothered. All you need to do is just to come up with you need to pick your regions, Asia, Europe, United States, then deploy as many database nodes as you need, and just don't forget to configure that partitioning. Like you might have, let's say, other types. Here I'm selecting the location, but your partitioning key can be anything. Let's say it can be country name, it can be data warehouse location, it can be anything that defines your application. And then the application just, the database decides how to store the data, where to read it from. And
most of the people, I never faced it myself and my team, but I heard that partitioning in Postgres, it's a little bit kill performance.
In Postgres, the partitioning is, there might be some, when you have too many partitions and when the Postgres, when you run, some people think that when Postgres, there are some of the operations, you think that you want to drop partition, you want to do something with a particular partition, but that might require a lock on the entire table. Let's say you're building some multi-tenant application and you decided to create a partition for that application for all of your customers. And then suddenly you have, let's say, hundreds of partitions associated. Then you need to do some job with one partition, and Postgres puts a table level lock, meaning that it will lock on your primary table and will lock all the other partitions. So there was some of the kind of gaps like this in the previous versions of Postgres. The Postgres community is very aware of this, and there's, like in the latest versions of Postgres, some of those notorious problems are solved. But here is, again, we are talking about geo-partitioning, and with the geo-partitioning, the approach is kind of unrelated to those use cases. Here is, I just have, let's say, one table, and my use case is that I have, let's say, 3 countries, 5 countries, or 10 countries, or some other locations, and I just want the database, route and store the data for me. So when you have, let's say, those 3 or 10 partitions, etc., it's unlikely that you will get into any of the issues with the partitioning.
Thanks.
Okay, thanks a lot. Thanks for coming and have fun building multi-region applications.